Hi everyone, today I'm going to talk about the three commonly used methods for the evaluation of wind turbine aerodynamics, including the blade element momentum (BEM), free vortex wake (FVW), and computational fluid dynamics (CFD). Traditionally, it is common to use the BEM theory to assess the aerodynamic behavior of a wind turbine. However, over the recent years, as shown here schematically, the size of wind turbines, especially the offshore ones, has undergone a dramatic increase due to substantial economic benefits. For instance, here we can see the 15 megawatt offshore wind turbine designed by the International Energy Agency (IEA), which has a rotor diameter of around 240 meters. The large blades of these huge machines are subject to large deformations due to increased flexibility and non-straight pre-bended blades. This, as a result, complicates highly the aerodynamics of wind turbines, where the low-fidelity BEM method is unable to predict accurately the machine behavior. This calls for aerodynamic models capable of capturing accurately the machine aerodynamics under large deformations of blades. Therefore, this has led to the development of FVW and CFD methods, which are capable of modeling more accurately the complex physics related to aerodynamics of large-scale wind turbines. Of course, CFD is able to provide predictions at a higher level of fidelity, but it comes at the cost of significant computational demand. On the other hand, FVW method, which is categorized as a mid-fidelity aerodynamic model, provides predictions with reasonable accuracy while maintaining the computational cost to an acceptable level. So what comes next is a detailed presentation of each of these methods. BEM. A wind turbine generates energy by extracting kinetic energy from the wind, as shown here schematically. This slows down the wind flow passing through the wind turbine rotor. Consequently, a boundary surface is created that separates the affected mass of air by the rotor from the rest of the air which is not affected. This boundary surface can be extended upstream of the turbine rotor all the way to downstream, forming a long stream tube of circular cross-section, as we can see here. The fact that no airflows can cross this boundary surface results in a mass airflow rate which remains unchanged along the stream tube at all streamwise positions. Considering that the air remains uncompressed, the cross-sectional area of the stream tube increases as the air flows downstream to accommodate the slower moving air. Due to the turbine presence, the approaching inflow air gradually slows down, and when it arrives at the rotor plane, the inflow velocity is somewhat smaller than the free stream velocity. As a result, the stream tube expands and the static pressure in airflow increases to absorb the drop in kinetic energy. When the air passes through the rotor, the static pressure undergoes a reduction. Thus, the airflow leaving the rotor has a pressure which is below the atmospheric pressure level. The air then travels downstream, which is referred to as the wake, with decreased velocity and pressure. To achieve equilibrium, the static pressure far downstream the wake region is recovered to the atmospheric level. Therefore, considering the far upstream and far downstream regions, while the pressure suffers no change, the kinetic energy reduces. The actuator disk concept. Here, the process of wind energy extraction by a wind turbine is explained using an actuator disk, as shown here in this figure. The actuator disk here represents the rotor plane area. As mentioned earlier, the stream tube cross-sectional area is smaller than the disk area over the upstream region of the disk, while over the downstream region, the stream tube cross-sectional area is larger. This changes in the stream tube cross-sectional area stems from the fact that mass flow rate remains the same everywhere. This mass flow rate can be calculated using this equation, rho times A times U, where rho is the air density, air is the cross-sectional area, and U is the air velocity. Considering that the mass flow rate remains the same everywhere in the stream tube, and so we can have this equation. Here, the infinity symbol refers to the far upstream region, D indicates the actuator disk, and W far wake region. The presence of the disk reduces the axial free stream velocity. The axial air velocity at the disk can be obtained using this equation based on the free stream velocity. Here, A is called the axial induction factor, momentum theory. The presence of the disk causes a reduction in the free stream velocity equal to U infinity minus UW, and a rate of change on the airflow momentum, which is given as this equation. This momentum change is associated with the force coming entirely from the pressure difference at the actuator disk. Therefore, we can write the following equation. The pressure difference on the left hand side can be calculated by applying the Bernoulli's equation to both upstream and downstream sections of the stream tube. Note that it is necessary to obtain separate equations, as the total energy over the upstream section is different than the downstream one. Based on the Bernoulli's equation, the total energy remains the same provided that no work is done on or by the fluid. Thus, for a unit volume of air, we have this equation. Therefore, over the upstream section, it can be written as shown here. If the flow remains incompressible, which means that the flow density remains unchanged, rho infinity equals rho d, and horizontal, which means h infinity equals hd, which means that h remains unchanged, then this equation here is reduced to this one. Similar equation can be obtained for the downstream section, as we can see here. Subtracting the last two equations gives this one. Therefore, substituting this equation into this equation yields this one, okay, from which we can obtain a relationship between the waked and free stream velocities, as we can see here, okay. As can be inferred from this equation, the momentum theory crashes for A greater than and equal to 0.5, because the wake velocity UW becomes 0 or even negative for A greater than and equal to 0.4. This therefore requires the application of an empirical modification, which will be treated later in this video. Power coefficient. To calculate the force in the air, one can write this equation: thrust force equals the pressure difference times the actuator disk area. Based on this force, the power extracted from the air can be calculated as shown here: the thrust force times the velocity at the disk, where a power coefficient can be defined using this equation, okay. Here note that the denominator represents the power available in the air, so the power coefficient is defined in terms of the axial induction factor. The Lanchester-Betz limit. To obtain the maximum value of Cp, this equation can be used. Therefore, we calculate the derivative of the power coefficient with respect to the axial induction factor, and then we put this equation equal to 0, which gives the following value for the axial induction factor. Hence, the maximum power coefficient value is as shown here, 16/27. This is the maximum power coefficient known as the Lanchester-Betz limit after Frederick Lanchester, 1915, a British aeronautical pioneer, and Albert Betz, 1919, a German aerodynamicist. This indicates the maximum extractable power from air. This limit has to do with the expansion of the stream tube upstream the actuator disc. In this regard, the stream tube cross-section at the position of upstream is smaller than the disc area. Thrust coefficient. The force acting on the actuator disc, as shown here, is also called the thrust force. The dimensionless form of this force is called the thrust coefficient and is given by this equation. Therefore, the thrust coefficient is also defined entirely as a function of the axial induction factor. This figure here shows the behavior of the power and thrust coefficients obtained from the momentum theory with respect to the axial induction factor A. Rotor disc theory. The wind energy conversion is carried out using a rotor with a limited number of blades rotating with an angular velocity omega about an axis normal to the rotor plane and parallel to the wind direction. The energy generation is performed by attaching an electrical generator to the rotor shaft. In addition to the thrust force, a torque is also exerted on the rotor in the rotation direction. The electrical energy is the result of the conversion of the work done by the aerodynamic torque on the generator. Wake rotation. The action of the torque over the rotor induces a rotational motion to the air in a direction opposite to that of the rotor. Therefore, by passing through the rotor, the air gains angular momentum, and so over the wake region, the air particles possess a velocity component in the direction tangential to the rotation, as well as an axial velocity component as shown here in this figure. The air particles acquire rotational motion solely by passing across the disk thickness. A tangential flow induction factor, A prime, is used to express the change in tangential velocity. The tangential velocity is 0 upstream the disk. However, right downstream the disk, the tangential velocity is 2p times omega times A prime. The direction of the tangential velocity is opposite of the direction of the disk rotation, as it is a reaction to the torque action. Angular momentum theory. Due to the rotor rotational motion, the tangential velocity changes with respect to the radial position. The same thing is also true about axial induced velocity. To understand this, consider an annular ring of the rotor disc with radius r and radial width delta r as shown here. The tangential velocity component imparted to the air is a result of the rotor torque acting on the annular ring as shown here. The whole disc is assumed to be composed of annular rings which act independently in imparting momentum to the airflow that passes through the ring. The torque acting on the ring can be estimated as the rate of variation of angular momentum of the air passing through the ring using this equation for delta Q, where here delta AD is the area of an annular ring. Thus, the rotor power output increment can be calculated using this equation. Delta P equals delta Q times omega. The rate of variation of the axial momentum given earlier based on the thrust force also yields the total power extracted from the air as shown here. Delta T times UD equals delta P, which is the rotor power output increment. Therefore, these two equations in fact must be equal, which gives the following equation. In this regard, we can define a new parameter, lambda r, as shown here. R, in fact, here the lowercase r is the radial position along the rotor span. The lowercase r times omega divided by u infinity. Here lambda r is defined as the local speed ratio. At the disk edge, where the lowercase r is equal to the rotor radius, the uppercase R, and lambda is equal to the uppercase R times omega divided by u infinity. It is called the tip speed ratio. Thus, this equation can be written as follows, okay? Knowing that the ring area, delta AD, is 2 times pi times the lowercase r times delta r, the incremental power is given by this equation. Here, the term inside the brackets stands for the air power flux through the annulus, while the term outside the brackets stands for the efficiency of the blade element in capturing the air power. Therefore, we can define a new parameter known as blade element efficiency, eta r, as shown here. Maximum power. As can be inferred from this equation, the values of A prime and A determine where the efficiency eta r will be maximized through differentiating this equation and putting the result equal to 0. From this procedure, we can obtain this equation, dA divided by dA prime. Okay, from this equation, it is possible to write this equation. Therefore, these equations together give this one. So it can be shown that the values of A prime and A, which maximize the incremental power, are as follows. Okay, note that the value of the axial induction factor A giving the maximum power is the same as that for the case without rotation. This value is constant over the entire disk, as you can see here. On the other hand, A prime is a function of the radial position. These values of induction factors lead to the same power coefficient of 16/27 obtained earlier. Rotor blade theory, blade element momentum theory. The blade element momentum theory uses two different theories, the blade element theory and momentum theory. The blade element theory divides the blades into several elements in which it is assumed that these elements have negligible interaction with the surrounding elements and operate as two-dimensional airfoils whose aerodynamic forces and moments can be estimated according to the local fluid flow characteristics. Accordingly, to calculate the total aerodynamic forces and moments acting on the blades and consequently on the turbine, these local forces and moments are summed along the span of each blade. Additionally, the momentum theory is used to calculate the induced axial and tangential velocities which affect the fluid flow characteristics in the rotor plane and as a result affect the forces and moments acting on the blade elements. Thus, the combination of these two theories results in the blade element momentum theory, which is an iterative process to calculate the induced velocity components as well as the aerodynamic forces acting on the rotor. As shown here, The span-wise blade elements of radius r and length delta r of the blades of a wind turbine rotor affect the rate of change of axial and angular momentum of the air passing through the annulus swept by the blade elements due to their aerodynamic lift and drag forces. These forces are also responsible for providing the force on the blade elements induced by the pressure drop due to the rotational velocity in the wake. Blade element theory. The forces acting on each element is calculated using the two-dimensional airfoil properties based on an angle of attack determined from the incident resultant velocity in the cross-sectional plane of the element. Note that it is assumed that the velocity component in the span-wise direction is equal to 0. At each radial position, the velocity components are expressed in terms of the wind speed, the flow factors, and the rotational speed of the rotor. Having the airfoil lift and drag coefficients in terms of angle of attack, the forces acting on the blades can be calculated for given values of induction factors A' and A. It is assumed that the turbine has B blades and R rotor radius. R in fact is the uppercase R is the rotor radius, each with a chord C and set pitch angle beta, where both the chord length and pitch angle may vary along the blade span. The rotor angular velocity and free stream wind speed are considered omega and U infinity. The tangential velocity of the blade element shown in this figure is r, the lowercase r times omega. Additionally, the wake rotational velocity is estimated as A' r omega, which results in a net tangential velocity at the blade element as 1 plus A' times r times omega. These figures show the relative velocities and forces on the blade element at radius r. Based on the upper side figure, the resultant relative wind speed to a blade element can be calculated using this equation. This velocity acts at an angle of phi regarding the rotor plane of rotation as shown here. The phi angle can be calculated using this equation based on this figure. Based on this equation, for a constant free stream wind speed, the inflow angle to the blade varies along the blade and it increases as one moves toward the blade root. This explains why the local blade twist angle in wind turbines is a function of span-wise position along the blade. It is largest close to the blade root while smallest at the blade tip. The reason behind this variation of twist angle is to make sure that the lift coefficients related to the blade elements are held constant and close to its maximum value everywhere, which minimizes the drag at operating condition. The angle of attack is estimated using this equation, alpha equals phi minus beta. Basically, the blade element theory assumes that the lift and drag forces acting on a blade element are the same as those acting upon an isolated identical airfoil element at the same angle of attack in two-dimensional flow. The lift force acting on a span-wise length delta r of each blade in the direction normal to the resultant wind speed w is thus as shown here, delta L, and the drag force is the in the same direction, okay, as W is estimated using this equation, delta D. Thus, the axial thrust force acting on an annular ring of the actuator disk is calculated using this equation based on the lift and drag forces, delta T, as shown here. In the same manner, the torque acting on an annular ring of the actuator disk, delta Q, is estimated based on the lift and drag forces acting on a blade element. The blade element momentum BEM theory. The BEM theory assumes that the change of axial momentum of the airflow passing through the annulus swept by a blade element is due only to the aerodynamic forces of that element. Thus, it is assumed that there is no radial interaction between the blade elements. Note that this is only true if no flow separation happens along the blade span. Equating the axial thrust force on each annular element obtained from both momentum and blade element theories gives the following equation for delta T. Additionally, equating the torque on the elements gives this equation for delta Q. The thrust coefficient can be reduced to this one, where mu equals the lowercase r divided by uppercase R is defined here. The torque equation is simplified to this one. The following parameters can also be defined, Cx and Cy, as you can see here. Thus, these equations can be solved to obtain the induction factors, right? The axial and the tangential induction factors as presented here. To obtain the values of induction factors, an iterative process is required. This is because the angle phi is also unknown at the beginning of the calculation. The chord solidity is another parameter. Chord solidity is defined as follows: sigma r. Determination of rotor torque and power. The torque is determined after the calculation of the induction factors using these equations, which are solved based on an iterative procedure. The process starts by assuming that the induction factors are initially 0, which leads to the calculation of the angle phi. Therefore, having this angle calculated, it is possible to estimate the values of lift and drag coefficients, which are used to calculate the new values for induction factors based on these equations. The iteration is continued until convergence is achieved. From this equation, the torque developed by the blade elements of span-wise length delta R is calculated, delta Q. The entire rotor therefore develops a total torque Q. Okay, using the total torque Q, it is possible to calculate the power produced by the rotor using this equation. P equals Q times omega. The power coefficient is estimated using this equation. Okay, solving the blade element momentum equations provides series of values for the power and torque coefficients, which are functions of the tip speed ratio. A typical performance curve for a modern high-speed wind turbine is shown in this figure. The maximum power coefficient occurs at a tip speed ratio for which the axial flow induction factor approximately is close to the Lanchester-Betz limit value of 1/3. At small values of tip speed ratios, the airfoil angles of attack are high, leading to stalled conditions. Stalling is much more probable to happen over the blade root because from practical constraints, the twist angle of a blade is not large enough over that region. As can be seen in this figure, over small values of tip speed ratio, there is a significant loss of power, which is attributed to blade stalling. Over both high and low tip speed ratios, drag is high and the axial induction factor is non-optimum, so the power coefficient is low. The optimum scenario would be for a turbine operating at a tip speed ratio close to that which gives the maximum power coefficient for all wind speeds. Breakdown of the momentum theory. The classical momentum theory breaks down for A greater than 0.4. This happens when the turbines experience large tip speed ratios. The momentum theory shows that for A greater than 0.4, the fluid flow in the far wake region starts to move upstream, which violates a basic assumption of this theory. However, physically, this is not possible, and what actually occurs is the large velocity jump u infinity minus uw gives rise to the generation of a highly turbulent wake in the downstream of the wind turbine rotor. At this condition, a much larger thrust force is exerted on the rotor than that predicted by the momentum theory. Glauert 1926 presents some experimental data for a whole rotor as shown in this figure, where the thrust coefficient predicted by the momentum theory as presented here is compared against the experimental data. As can be seen, a large deviation exists between the thrust coefficients obtained from experiment and momentum theory for A greater than 0.4. Based on the experimental data shown in this figure, Glauert provides an empirical solution by proposing a parabolic function to calculate the thrust coefficient for A greater than 0.4. It is also possible to fit a line to the experimental data as shown in this figure. Here, CT1 is the empirical value of the thrust coefficient for A equals 1. Additionally, this line, which must be tangent to the momentum theory curve and passes at the transition point of AT. Therefore, for A greater than AT, the usual momentum theory is replaced by empirical equations. Note that for A greater than 0.4, the turbine is operating at heavily loaded conditions, which are challenging to model correctly. Thus, the empirical treatments presented here must be regarded as approximate solution at best, which are much better than the original momentum theory. The good news is that the axial induction factor remains close to 0.33 for a wide range of operating conditions of a well-designed blade. The effects of a discrete number of blades. The BEM theory assumes that every fluid particle that passes through the rotor disc interacts with the blade. In other words, the momentum loss is the same among all fluid particles. However, due to a limited number of blades of a wind turbine, there will be almost no interaction between the majority of the fluid particles and the blades. Tip losses. One of the key assumptions of the BEM method is that each section is assumed to be independent of the neighboring sections. Note that this assumption is suitable for the inboard radial sections of the blades. However, it is less valid for the outboard radial sections due to the noteworthy interaction that exists between these sections. In particular, there is a significant movement of the fluid particles from the high pressure side of the rotor toward the low pressure side, which is observed as the tip vortices as shown here. Therefore, the vortex shedding from the blade tips is inevitable. These vortices give rise to the formation of numerous vortical flow structures in the wake region, which have a significant influence on the induced velocity distribution. This influence is most noticeable close to the blade tips, an area that plays a significant role in the power production of a turbine. The tip vortices cause a decrease in the lift force and thereby the generated torque acting on the outboard sections. To take into account the influence of tip vortices, Pranto developed a tip loss factor as shown here, where the lowercase f is defined using this equation. Note that here B denotes the number of blades, capital letter R, the rotor radius, and lowercase letter r is the local radius on the rotor. The tip loss factor is introduced into the differential thrust and torque equations as shown here. As a general rule of thumb, for lowercase r divided by uppercase R smaller than or equal to 0.6, f is approximately 1. However, for lowercase r divided by uppercase R greater than 0.6, f is smaller than 1. Thus, as one approaches the blade tip, the tip loss factor decreases significantly, which corresponds to an increase in the induction factor in this area. This, as a result, reduces both the relative wind speed and the angle of attack. That is the reason why the aerodynamic forces undergo a decrease close to the blade tip. The axial and the tangential induction factors A and A prime are also modified, as we can see here. It is shown that the accuracy of the Pranto's factor decreases with both a decrease in the number of blades and an increase in the tip speed ratio. Note that the Pranto tip speed factor offers a simple and efficient solution to a complicated problem. This correction accounts for both the effects of discrete number of blades and the induction factors being zero at the edge of the rotor disc. Root losses. Root losses, which are also referred to as the hop losses, are necessary to correct the induced velocities due to the vortex being shed from the blade root, as we can see here. The hop loss factor is calculated using nearly the same procedure as that used for the calculation of the tip loss factor, as shown here, with a minor modification introduced into the lowercase letter f shown here. A given blade element may be affected by both the tip and root losses. For these cases, the total correction factor is defined as the multiplication of both the hop loss and tip loss factors. Then this total correction factor is used to modify the induced velocity. Stall delay. It is shown by many researchers that for a rotating blade compared to the same blade under static conditions, the stall occurs at a larger angle of attack. This phenomenon is called the stall delay, which leads to an increase in the rotor power output. The stall delay effect is more pronounced close to the blade root and decreases with an increase in the radius. It is agreed that the Coriolis and centrifugal forces originating from the rotor rotational motion reduce the adverse pressure gradient acting on the flow over the downwind surface of the blade. As the angle of attack increases, the flow separation occurs due to the adverse pressure gradients developed on the blade downstream surface from the leading edge toward the trailing edge. Consequently, stall occurs, giving rise to loss of lift and a dramatic increase in the pressure drag. When the flow remains attached to the blade surface, no evident difference exists between two-dimensional flow conditions and rotating conditions. When stall takes place, the flow over the separated region is subject to centrifugal force exerting a radial motion toward the blade tip on the flow. Prior to occurrence of stall, the radial flow caused by the centrifugal forces may reduce the displacement thickness over the boundary layer, increasing the resistance against separation. In this regard, the following figures here, they show the pressure distribution over static and rotating blades at three span-wise locations. The lowercase r divided by uppercase r equals to 0.3, 0.55, and 0.75 at similar tip speed ratio. The flat pressure distribution over the downwind surface of the static blade clearly shows that the flow separation has already taken place for the span-wise locations of 0.3 and 0.55, while the rotating blade has not undergone any flow separation. Instead, the pressure values have increased significantly over the downwind surface of the blade compared to the static blade. This indicates that the stall delay phenomenon is also responsible for an increase in the lift force acting on the blade. For instance, this figure shows schematically the lift force coefficient against angle of attack for an airfoil over rotating three-dimensional case and static two-dimensional case conditions. A clear difference can be detected between the two cases, with the rotating one being much higher over a considerable portion of angles of attack. Thus, for an accurate assessment of a wind turbine aerodynamics, it is crucially important to crack the two-dimensional airfoil data to account for these three-dimensional effects. Scud wake correction. The BEM method was originally developed for fluid flowing normal to the rotor plane. However, there are cases in which the wind turbines operate at an angle of yaw relative to the incoming flow, which creates a Scud wake behind the rotor. In this regard, usually the following equation is used to take into account the Scud wake effect on the induced velocity. Here, psi is defined as the azimuth angle, as shown here in this figure, and chi is the wake skew angle, which is also shown in this figure. Note that this correction is applied to each blade element rather than the rotor, which was the main intention of the original model. The relation between the wake skew angle and the yaw angle is expressed using this equation. Here, gamma is the rotor yaw angle, as shown here in this figure. This equation here can be approximated as a simpler equation, as we can see here, where chi is related to omega using this equation. Final remarks on BEM. As can be inferred from the previous sections, to improve the predictions given by BEM method, several corrections have been introduced to account for the effects such as blade tip and root losses, a finite number of blades, three-dimensional stall delay, dynamic stall, yacht wind turbines, unsteady loading, and dynamic inflow. However, as mentioned earlier, the modern large-scale wind turbines, they are subject to large blade deformations due to increased flexibility and non-straight pre-bended blades. Note that the large blade deformations of modern large-scale wind turbines may also give rise to an interaction of the blades with their own vortices, which is a violation of basic assumptions of the BEM method. The basic assumptions of BEM model are further violated when these large-scale wind turbines are placed on top of a floating platform, suffering large movements due to coupled loading from wind, wave, and current. This requires the use of aerodynamic models capable of capturing accurately the machine aerodynamics under such complex conditions. In this regard, free vortex wake FVW is capable of modeling these complex physics while maintaining the computational cost to an acceptable level. The methods based on FVW, while remaining less computationally expensive than CFD, they are capable of capturing these complex physics. Free vortex wake. The wind turbine size has undergone a dramatic increase due to substantial economic benefits. However, this requires the use of aerodynamic models capable of capturing accurately the machine aerodynamics under large deformations of blades due to increased flexibility and non-straight pre-bended blades. In this regard, free vortex wake FVW is capable of modeling these complex physics while maintaining the computational cost to an acceptable level. The large blade deformation may result in a swept area that differs remarkably from the rotor plane. This difference is a violation of the basic assumptions of the BEM method, which revolves around actuated disk assumptions valid only for axisymmetric load distribution over the rotor plane. Further, the large blade deformations may also give rise to an interaction of the blades with their own shed vortices, which is again a violation of basic assumptions of BEM method. The basic assumptions of BEM method are further violated when these large-scale wind turbines are placed on top of a floating platform, suffering large movements due to coupled loading from wind wave currents. The methods based on FVW, while remaining less computationally expensive than CFD, are capable of capturing these complex physics. The FVW belongs to the vorticity-based methods such as the vortex lattice method, assuming that the flow is inviscid, incompressible, and irrotational, and have long been used in the field of wind energy. The FVW method is used to solve the turbine wake based on a time-accurate manner in which the convection, stretching, and diffusion of vortices are captured. This is performed using a Lagrangian approach, able to discretize the turbine wake into Lagrangian markers defined as a function of wake age, zeta, and azimuthal blade location, psi, as shown in this figure. A wide range of methods are available for the representation of the wake using Lagrangian markers, including the hybrid lattice filament method used within the OpenFast code as shown in this figure. Over the near wake region, a lattice method is used as shown here. A user-defined angle is used to specify the near wake span, which is usually assumed to be delta psi equals 30 degrees. This angle may not be sufficient for challenging operating conditions, for example at high thrust conditions. As we can see here in this figure, the near wake region is followed by instantaneous rolling up of the wake into tip vortices, which is considered the principal flow characteristics over the rest of the wake. Straight line vortex filaments with second order accuracy are used to connect the Lagrangian markers together. As we can see here in this figure, the initial wake is assumed to have a helical structure and is defined based on the rotor angular velocity omega and predetermined time step delta t, as we can see here. D psi equals dt times omega. Considering that the wake moves and distorts as the markers convect downstream, the wake structure then changes. A vortex filament motion is expressed using this equation. Here, r as a function of psi and zeta is the position vector of the Lagrangian markers, and v as a function of r and t is the velocity vector. Based on the chain rule, this equation can be written as shown here. Note that d psi is defined as dt times omega, and d psi equals d zeta. The left hand side of this equation is solved numerically based on a predictor character scheme for the vortex filament location. The different operators on the left hand side are approximated based on Taylor series expansions. For instance, in OpenFast code, the first term on the left hand side is discretized using a 2 steps backwards scheme, while the second term is approximated by central differencing. Additionally, the right hand side is approximated by computing the average value of the velocities surrounding the point about which the Taylor series expansion is applied. The final discretized equation, which is referred to as a predictor and corrector equation, is used to compute iteratively the wake position for all the Lagrangian markers based on the previous values of wake positions. The velocity on the right hand side of this equation is the sum of two components, the free stream and induced velocities. In case of a floating wind turbine, one must also consider the velocity induced by the platform motion. Each straight line filament creates an induced velocity at point K, which are calculated based on the Biot-Savart law as presented here. Here, gamma is the filament circulation strength, L is the vector used to connect end point locations of filaments, and R here is the normal distance from L to point K. The factor F nu, which is used to account for the viscous effect on the vortex core, can be modeled using various methods. The blade itself can be represented using either a lifting line or lifting surface. However, a more attractive option is the use of the Weisinger L blade model, which has demonstrated to give more reliable results than the lifting line model, with a computational cost much lower than the lifting surface model. Based on a blade model, the circulation along the blade span is computed for airflow elements by discretizing the blade into a finite number of two-dimensional airflow elements and using the Kara-Zhukovsky theorem as shown here, and then connection to the wake is performed by dependence on the induced velocities. Here delta F is the sectional lift force and V is the magnitude of the velocity vector. CFD. The CFD methods, by resolving all the geometric details, have shown a great potential for the accurate prediction of the aerodynamic behavior of a wind turbine. Unlike BEM and FVW, which rely on external input of aerodynamic loads as well as semi-empirical corrections for considering three-dimensional effects, dynamic stall, etc., CFD method naturally accounts for all these effects. Another important advantage of CFD compared to BEM and FVW is the better ability of CFD to capture the turbulent wake behind a turbine, which generates considerable transient loads on the downstream machines. The turbulent flows around wind turbines are governed by the continuity and Navier-Stokes equations, which for incompressible Newtonian fluids in Cartesian coordinates are written as shown here. Here the uppercase UI are the instantaneous velocity components at a point in space xi, which are the Cartesian coordinates, and time t. P here is the static pressure, rho is the fluid density, nu is the fluid kinematic viscosity, Sij is the instantaneous strain rate tensor, which is expressed in terms of the gradient of instantaneous velocity components as shown here. These equations are just Newton's second law written for a continuum in a spatial reference frame. Together, they relate the rate of change of momentum per unit mass, rho times ui, which is a vector quantity, to the surface and body forces. CFD typically uses the finite volume method, which is one of the most popular methods for the discretization of the governing equations to solve the governing equations. The popularity of the finite volume method in CFD stems from the fact that it reflects the physics and the conservation principles of the fluid flows, such as the integral properties of the governing equations. In this method, the computational domain is discretized into a finite number of control volumes over which the integral form of the governing equations is discretized. The discretized governing equations in the whole computational domain form a system of algebraic equations as shown here, Finally, this system of algebraic equations is solved to obtain the solutions. The general workflow of the finite volume methods is presented here for a CFD simulation of a horizontal axis wind turbine. 1. The desired computational domain is precisely specified. 2. The computational domain under consideration is divided into computational grids using a finite number of control volumes or cells. 3. Integral equations are discretized over each of these control volumes. 4. Discretized equations that form a system of algebraic equations are solved. For more information on this about the finite volume method, you can watch the video in my channel entitled Finite Volume Method, a thorough introduction. You can access the video using the link given at the top right corner of the screen. CFD often uses 3 different methods for the solution of the Navier-Stokes equations for turbulent flows: direct numerical simulations, DNS, large eddy simulations, LES, and Reynolds average Navier-Stokes equations, RANS. Before I explain the difference between these methods, it is worthy to have a general idea of the degree of accuracy of these methods in the prediction of a turbulent jet, which is shown in the following picture. As can be seen, DNS provides a very accurate model-free representation of the unsteady evolution of the turbulent flow. In fact, a properly designed DNS resolves all the temporal and spatial turbulence scales down to the Kolmogorov scale without using any modeling techniques. For a CFD computation, in order to resolve all the turbulent flow structures, the control volume size and time step must be of the same order as the Kolmogorov length and time scales respectively. This is exactly what DNS does. Here I'm going to give you an example to have an idea about the computational cost of a DNS simulation. A typical flow domain of 0.1 by 0.1 meters with a high Reynolds number turbulent flow might contain eddies down to 10 to 100 micrometers. Let's put it into context. Here I'm showing an eddy with the size of 100 micrometers. To resolve this eddy, we need at least 4 mesh cells as shown here. From the velocity vectors shown here, it can be concluded that this is the minimum possible resolution we can use to resolve an eddy. This actually allows us to give a numerical representation of an eddy. This means that the minimum spatial resolution that we can use for this case is 50 micrometers, which is equivalent to at least 10 to the power of 7 mesh cells for a computational domain as small as 0.1 by 0.1 meters. The challenge does not end here. The frequency of these small eddies is on the order of 10 kilohertz, so we would need to discretize the time into steps of about 100 microseconds. The DNS method is computationally very expensive, not only due to the space and time scales mentioned above, but also in order to accurately resolve the small scale motion. It needs to employ high-order discretization schemes that most general-purpose commercial CFD solvers do not have such schemes. For these reasons, alternatively, less demanding turbulence modeling methods are employed. Large eddy simulation, LES, employs a filtering approach on the basis of the control volume size. LES, in fact, resolves the important large eddies while it models the influence of smaller eddies on the large eddies. LES is computationally less expensive than DNS, but it still needs fine mesh and small time step to appropriately resolve the flow. Finally, we have the Reynolds average Navier-Stokes equations, which are represented as the RANS. Okay, The RANS is less demanding in terms of computer resources than the previous two methods. The RANS equations arise from ensemble averaging, not time averaging of the Navier-Stokes equations, in which the instantaneous flow variables are decomposed into the mean and fluctuating parts using the Reynolds decomposition technique. In these equations, the turbulence effect is represented through the Reynolds stresses, which are modeled by turbulence models. In other words, the RANS equations provide the mean flow characteristics, where the turbulence effect on these mean flow characteristics is accounted for through turbulence modeling. The difference between DNS, LES, and RANS can also be explained using the turbulent kinetic energy spectrum as follows. A properly designed DNS resolves all the temporal and spatial turbulence scales down to the Kolmogorov scale without using any modeling techniques. LES resolves the important large eddies while it models the energy transfer from large to small scales. Note that the cutoff wave number separating the resolved and modeled length scales is usually found in the inertial range prior to the dissipation range. And finally, we have the RANS method, where the turbulence is accounted for by modeling the effect of all the turbulence scales on the mean flow. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.